Chapter number 5, acid, bases, and salts. We're starting with acid. So what's an acid? The word acid is actually applied to the substance with a sour taste. That's an old name. Well, we define acids in a much different way. What we're going to start with is not the definition of the acid itself, instead, the introduction with many common acids. What we know for sure is that acids are usually corrosive. They can eat their way through skin or clothing or stonework or even metals. So let's go through with a few acids. The table 5.1 at the bottom of page number 120 is what we're going to start with. The acids are defined in the two main categories, the organic acids and the mineral acids. We're starting with organic acids. Organic acids are the ones that are usually commonly found through the organic system. They're composed of carbon. They're based on carbon, actually. Ethanoic acid, the formula for which is CH3COOH. It's actually a weak acid, and it's usually found in vinegar. Vinegar is a flavoring agent and is commonly used in foods. Methanoic acid, it's COOH, which is weak and is found in ant and nettle stings. It's also used as a keter descaler. We'll come to this point a little later in around 5.3 or 5.4 of this chapter. Lactic acid has a big formula. Well, let me tell you, you're not supposed to memorize this formula, so you can simply cut it out. This one is also weak acid, and it's usually found in sour milk. Moving on, citric acid, as you heard the name, is a part of citrus fruits. The formula, again, you're not supposed to do, is a weak acid found in apples, lemons, oranges, citrus fruits like tomatoes, etc. Then we have the next category, that is mineral acids. Now, carbonic acid is the first one of them. It's H2CO3. Let me tell you, this T is just a mistake. So the formula is just H2CO3. Just cut the T out. Weak and found in fizzy soft drinks. Coca-Cola, Pepsi, name the drink, it contains it. Hydrochloric acid, HCl, we already know that's a strong acid that's actually found as a dilute acid in human stomach. Apart from that, it's also used to clean metal surfaces. Nitric acid, HNO3, is a strong acid used in making fertilizers and explosives. Sulfuric acid, H2SO4, the king of acids. Strong acids used in car batteries, used in other kinds of batteries, used in making fertilizers, paints, detergents. The list goes on. It is actually used to make a lot of stuff. Phosphoric acid is the last one on the list. H3PO4, strong acid used in anti-rust paints and also used in making fertilizers. Now, if you take a look, you will find out that most of the organic acids are the weak one, while most of the mineral acids are strong one. That's actually true. So if we move on with the acids, and I'm going to go with a little abrupt order as a little unaccordingly with the book. The book continues with the indicators. I'm not going to do that. I'm actually going to move to the next page, and I'm going to continue talking about the acids. So if we move on to page number 122, you will find that acids actually are defined in a different way. Just a second. Let's see. Let's get to the definition of the acid so that I can finish it up before I move on to any other kinds of. There you go. Actually, the definition of the acid is present at the page at the bottom of the page 124. So we define acid as a substance that dissolves in water and produces an excess of hydrogen ions, H positive, and the solution can be defined in three ways. One, it contains an excess of H positive ions in water. Two, it can turn the blue litmus paper red. 3, it has a pH lower than 7. And opposingly, alkali is a substance that dissolves in water that produce hydroxide ion, OH negative ions. The solution contains an excess of OH negative ions as its first definition. The second definition is that it can turn the red litmus paper blue. And the third definition is its pH is higher than 7. So let's go a few pages back, and according to these definitions, understand what pH is or what is litmus paper. To begin with that, you would find that organic acids or mineral acids are all taken with the help of indicators. So let's start with indicators. What are indicators? Indicators are actually colored substances, and they are extracted usually from plants, And indicators change their color, their appearance, whenever the medium is changed from acid to alkaline or neutral. There is an easy study tip given over here that acids are usually red on the litmus paper and bases are usually blue on the litmus paper. The litmus paper has to be damp in order to work. So in order to work with most of the indicators, let me tell you there is a table 5.2 at the top of page number 121, which gives us the idea. First of all, we have litmus solution. Let me tell you, it's not litmus paper as an indicator, it's litmus solution. Its color in acid is red, its color in neutral color is purple, while in alkali it's blue. Phenolphthalein, or you can also pronounce it as phenolphthalein, has a colorless appearance in both acid and neutral colors, and it's actually pink in alkaline medium. The only disadvantage of phenolphthalein is its color, that it does not give you a different color in acidic and neutral medium. So you can't actually get to know in colorless portions whether it still is neutral or is acidic. So that's a disadvantage with phenolphthalein. Further on, when we're going to discuss titration in this chapter, we're going to know that phenolphthalein carries this disadvantage to a point where it's difficult for us to determine the pH. Next up is methyl orange, which is red in acidic medium, orange in neutral medium, and yellow in alkaline medium. You're supposed to memorize this entire table. You were supposed to memorize table 5.1 as well, but you can simply skip the formulae of lactic acid and citric acid in those tables. You can memorize the rest. Now, these are different indicators, they show different colors in acidic or alkaline medium, even in neutral medium, but these are not the standard when it comes to indicators. When we talk about indicators, universal indicator is actually the standard. The name is universal indicator. The name is also a full range indicator. We also call it a rainbow indicator. And that's because it imitates the rainbow. It's actually a mixture of different dyes, and it gives different colors with different mediums. Now let's take a look. You would see that it gives you from pH 1 to pH almost 3 the red color. And then there is a mixture of red and orange in between. And at 4, it gives you an orange color. 5 to 6, it gives you a yellow color. 7 or neutral is green. Then there is blue when we start with very weakly alkaline, or weakly alkaline is indigo, and then there is violet, a big range of violet, all the way from 11 to 40. We actually categorize these as strongly acidic, weakly neutral, weakly alkaline, or strongly alkaline. That's a good way to bifurcate them, and you would also see different colors in different shades at the bottom. Universal indicator is actually a very good one because it can give you a very long range and different colors for different mediums, giving you a very good idea of the pH or the medium. Let's talk about the pH. I've been using this word, let's define it and let's discuss it. The pH scale. P actually stands for potence. Potence means potency. Potency means concentration. H actually comes from hydrogen. The word is potence hydrogen, which means the amount of hydrogen ions in the system. That comes from the very start when humans were talking about acids as useful substances and were trying to discover its properties. Rules for the pH scale. The pH scale is simple. The pH scale goes from 0 all the way to 14, and it is simple numbers. Acids have a pH less than 7. The more acidic this pH, the more acidic a solution, lower the pH. Neutral substances such as pure water have exactly a pH of 7. And alkalis have a pH greater than 7. The more alkaline a solution, the higher is the pH. The closer value is to 40. Now, how do we calculate the pH? It's pretty easy. In order to calculate the pH, we can use the universal indicator paper or the universal indicator solution. And as we have studied on the previous page, apart from the bifurcations of colors or of the mediums, you would see numbers of pH from 0 all the way to 40. So these are the pH numbers that we were talking about, and it's easily bifurcable in this portion. Now, we can use a digital pH meter as well. A digital pH meter actually has a preference on top of every kind of indicator. Why? A digital pH meter has its value up to 2 decimal places of accuracy, and this kind of accuracy is something that no kind of paper can give you, not even the universal indicator paper. So pH meter is considered to be on the top of list when it comes to accuracy. It has a simple electrode. Dip the electrode in the solution, it would give you the pH. And remember, it can only work for solution. It does not work for solids. So the system has to have some water, has to have a slight amount of solvent or aqueous solution. And for the most common aqueous solutions, you will see a big table over here, table 5.3, where they talk about different things. Now, let me tell you, you're not supposed to memorize this table. This table is not for memorization, but definitely this table is going to give you a very good idea where different things lie. For example, hydrochloric acid has a pH of 0. It doesn't have a pH of 0 in human stomach. Gastric juices have a pH of 1. Lemon 2.5. Moving on, acid rain is 5.6. These are the important ones. If you can memorize these, it's better to memorize these. Any of these. Actually, the ones I'm circling are the more important ones. I agree. Acid rain is 5.6. Rainwater is commonly 6.5. Pure water or sugar solution is exactly neutral, 7. And the blood has a pH of 7.4, which is very, very slightly alkaline. Now, you would see that as we go down the list, the more alkaline or strongly alkaline the substance is. Toothpastes are commonly 9 at the pH scale. We use them commonly, and yes, that's the purpose why we use them, that they are alkaline. So, apart from that table, let's talk about the acid and alkaline solutions and talk about the importance of hydrogen ions, because that is helping us with the pH. There you go, the potent hydrogen word is written over here. Now, hydrogen ion solutions in acid solutions make the litmus go red. Hydroxide in alkaline solutions make the litmus go blue. Now, take a good look at this specific portion. This figure is going to give you a very good idea how we work with acidic, alkaline, or neutral solutions. Take a look. Pure water was neutral. Why? Number of H positive ions and OH negative ions are equal to one another, hence the formula H2O, and the pH is 7. This is a perfect balance. When both balance goes down in the favor of acidic solution, we have more H positive ions. Inversely, when the balance goes down in the favor of alkaline solutions, we have more hydroxide or OH negative ions. In case of an excess of H positive ions, the pH is lower than 7 and the litmus is turned from blue to red. Vice versa, if it goes down in the favor of hydroxide ions, the pH is higher than 7 and the litmus paper turns from red to blue. So this gives us the key definition of acid and alkali. We can define it in terms of excess of ions, or which color litmus paper is going to turn to, or what kind of pH it's going to have. But there is one more important point over here that we need to keep in mind, is that acids and alkalis actually give different ions in solution. You would notice something common in all the acids, and that are H positive ions. No matter what kind of negative ion it gives, fluoride comes from hydrochloric acid, nitrate comes from nitric acid, sulfate or hydrogen sulfate comes from sulfuric acid, but all of them consist H positive ions, hence the word acid. You would find something common in alkalis, and that is OH negative or hydroxide ions. Pretty easy, no matter it contains sodium positive or potassium positive or calcium positive or even ammonium positive ions, but it definitely consists of the negative hydroxide ions. All right, so that's the way to bifurcate the ions in an acid or an alkali. Remember, bifurcation of ions for different acids or alkalis, as some of them are written over here and not all of them, has been a part in past papers. So you should be able to bifurcate any acid or alkali into ions. Let's say if I talk about phosphoric acid and the formula for which is H3PO4, we should be able to bifurcate it into ions. It can give you H positive ions and it can give you the negative phosphate ions. So we should be able to see that it's an acid, it would give you H positive, and it is going to give you any negative ion as per the acid itself. So moving on, next up is importance of water. It's pretty easy. Due to water, an acid is an acid, an alkali is an alkali. Without water, the acid or alkali might not be able to dissolve in the solvent and might not be able to dissociate into H positive or OH negative ions respectively. If that doesn't happen, the acid will never be able to prove it's an acid, and the alkali will never be able to prove it's an alkali. Remember, acids act like acids or prove themselves acids when they decompose and give hydrogen ions. Alkalis, on the other hand, prove themselves as alkalis when they decompose and give hydroxide ions, like they do in this table, table 5.4 on the top of this page. So water has a very important, significant role over here. Inside water, the acid dissociates and prove itself an acid, and the alkali dissociates to prove itself an alkali. So that's the importance of water right there. Moving on, this completes 5.1 and 5.2 for us. For 5.3, next topic is oxides. It consists of metal and non-metal oxides. (5.3) is all about oxides. Actually, oxygen is a very reactive non-metal. We can call it the second most reactive non-metal to fluorine in the periodic table. The first one is fluorine. Now, being more reactive means that it can react with almost anything around the periodic table, and that's actually true for oxygen. Oxygen can react with most of the non-metals as well as most of the metals. And when oxygen reacts with an element and it forms a binary compound, and a binary compound means oxygen and one other metal in a compound, that means they only contain two compounds, two elements in the compound. That's why we call it binary compounds. They are known as oxides. And oxides are very important when we talk about their reactivities or specifically in relation with acids, bases, alkalis, or this chapter. As you can see, oxygen can react with most of non-metals. You would see a reaction with sulfur over here, a reaction with carbon over here. So what we're going to do is that we're going to discuss oxides as a special topic, and we are also going to bifurcate it to different types. To do that, I'm going to start with the bottom of page number 126. At the bottom of page number 126, you would see that I'm going to add something to it. Oxides that are actually compounds of oxygen. Binary compounds of oxygen, to be exact, are divided into two categories, metal oxides and non-metal oxides. And I think it's pretty simple. The name itself suggests that metal oxides are reactions of metals with oxides, and non-metal oxides are the reactions of non-metals with oxygen. Now, metal oxides are further of two types, basic oxides and amphoteric oxides. Non-metal oxides are further of two types, the neutral oxides and acidic oxide. You would see many elements reacting with oxygen. Here we have carbon, sulfur, nitrogen, phosphorus, silicon, hydrogen, carbon, nitrogen, zinc, aluminum, calcium, magnesium, copper, potassium, sodium, iron. So we see many metals and non-metals reacting with oxygen and forming oxides. Now, what do we have to do with classifying the oxides in the chapter of acids and alkalis? Let's discuss that. We're going to discuss that with the help of the table on the top of page number 146. When we talk about this table, we are going to go with two things in this table. We're going to talk about the chemistry as well as we're going to talk about our visual observations. This table is all about reactions of certain elements with oxygen. When a metal or a non-metal reacts with oxygen, what happens? What happens in terms of the chemical purity, and what happens to what we see in front of our eyes? I mean, the visual observations. So we're going to cover all of that, and we're going to start off with non-metals. We're going to move on to metals. This is a table. It only consists words, maybe a few formulae, but it never consists of any equation. So I'm going to fill this table up with equations which have been a part of past papers, which are actually a part of this book too. But those equations are scattered all over the book. Chapter 1, Chapter 3, Chapter 4, this chapter, Chapter 7, Chapter 8, Chapter 9. So it's as it is scattered over the book, it's difficult to gather those pieces of information or to be good in a single grasp of the book. That usually happens right before the actual IGCSE papers. But in order to get you over there, we're going to work our way by collecting and writing all the information in one place. So continuing, we're going to start off with sulfur. Sulfur actually burns with a bright blue flame. I think we're going to scoot to the previous page to see the picture. There you go. Sulfur is of yellow color. When we burn it, it burns with a bright blue flame. This is something that is so obvious in terms of visual observations that when we burn the sulfur, the flame itself speaks for it. We quickly get to know that we are burning sulfur even if we don't know what compound we were burning in the start. So it burns with a bright blue flame. This is the visual observation. It produces a colored gas that is sulfur dioxide. Let's write the reaction. This is S plus O2 that gives us SO2. Now, effect of adding water in testing with litmus. Remember, we can't test a litmus paper for solids. It can only happen for aqueous solutions in specific. Now, sulfur dioxide is soluble in water. Let me explain. The reaction that we need to understand is this. And this one is actually sulfurous acid. ROU as sulfurous acid. That's why the litmus paper turns from blue to red. That's why it dissolves. So there is actually background chemistry involved. This chemistry and these equations have been a part of past papers, but they're not written over here. So we're going to write it with every metal or non-metal that we study. Moving on to phosphorus. Well, let me give you a small point over here too. Sulfur dioxide, upon further oxidation, can be converted into sulfur trioxide, which is, by the way, also soluble in water, actually more soluble than even sulfur dioxide, and produces the acid H2SO4, which we know by the name of sulfuric acid, which also happens to turn the litmus paper from blue to red. Both of these equations have been a part of past papers. Moving on, the next non-metal in the list is phosphorus. It burns with a yellow flame. It produces a white solid, phosphorus 5 oxide, P2O5. Actually, P4 reacts with 5O2 and it gives us 2P2O5. Phosphorus exists in the form of P4. You can simply write a P over here. It also exists in the form of P. All right. So we can write P4, we can write simple P. Both ways, the equation will be considered as correct and it would form phosphorus 5 oxide, the formula to which is P2O5. Now, P2O5 is actually pretty much soluble in water and it gives us H3PO4 phosphoric acid. Phosphoric acid, which we just studied a couple of pages ago. So phosphoric acid is also a strong acid, as we have previously studied, and so it can easily cause the blue litmus paper turn red. This equation is not balanced, my bad, it's H2O. I by mistake wrote it H3O. Actually, this is going to be, I think, like this, and this is going to be 3H2O. I think that balances the equation. So it's P2O5 plus 3H2O gives us 2H3PO4. I think that balances the equation. Moving on, next up on the list is carbon. Carbon does not give us any characteristic flame. Instead, it itself glows red, which, by the way, you might have seen in barbecues and bonfires. So it produces a colorless gas, carbon dioxide, which dissolves slightly and slowly turns the litmus paper red. So it's C plus O2 giving us CO2, and actually CO2 can dissolve in water to give us the only weak acid in the category of mineral acids, that's H2CO3, and the name of which is carbonic acid. Right? Now, I usually tell my students that we actually are missing a non-metal over here. Just because it does not give you a visual observation while reacting doesn't mean we should leave it over here. So I'm going to add one more non-metal to the list. The name of the non-metal is nitrogen. And I think you're already familiar that it doesn't give you any characteristic flames or colors while reacting. How it reacts is actually N2 plus O2. It gives us 2NO. That's nitrogen oxide or nitrogen monoxide, which is actually insoluble in water. However, this 2NO can further react with O2 to form 2NO2, and this 2NO2 is actually soluble in water in the presence of oxygen, like that, and gives us the nitric acid, which of course is going to turn the blue litmus paper red. This completes all the nonmetals for us, at least the ones that are included in IGCSE syllabus. Sulfur, phosphorus, carbon, nitrogen. And you would notice that all of them dissolve in terms of their oxides, except for NO, or let me tell you, CO also is insoluble. Apart from carbon monoxide and nitrogen oxide or nitrogen monoxide, both of which are insoluble, the rest of the oxides dissolve in water, either slowly or fast, and they can turn the blue litmus paper red. You would see they're all forming acids when the oxides are dissolved into water. That's what the oxides have to do with acids. These oxides, as soon as they dissolve in water, react with water to form an acid. And of course, that acid is going to give its own pH, which is less than 7, and also will be capable of turning the blue litmus paper to red. Let's move on with the metals. Sodium comes first. It burns with a yellow flame. It gives us the white solid Na2O. I think the reaction is pretty easy. For Na plus O2 gives us 2Na2O. Sodium oxide, which dissolves quickly and turns red litmus paper blue. That's because Na2O can dissolve in water to form So I was actually talking about sodium, and I was saying that sodium burns with yellow flame, and I was writing the equation that sodium can react with oxygen to produce the sodium oxide, Na2O, which is actually soluble in water, and Na2O actually, when dissolving in water, produces an alkali by a proper reaction, that is 2NaOH. That's an alkali by the name of sodium hydroxide, and is easily capable of turning red litmus paper to blue. Up next is magnesium. It does not give a flame color. Actually, it burns with a bright, flashy white light. Not the flame, white light. We shouldn't call it a flame because in the next parts of the book, like in chapter number 8 or chapter number 9, we call it bright, flashy white light and not the flame color. It produces a white solid, that is magnesium oxide. The reaction goes something like this: 2Mg plus O2 gives us 2MgO, but it dissolves slightly. MgO can dissolve in water very slightly to produce the hydroxide, which is actually MgOH twice. Unfortunately, this doesn't dissolve much, so it dissolves slightly and turns litmus paper going from red to blue very slightly. Next up is calcium, which burns with a red flame, and this is actually the characteristic of calcium as well. It produces a white solid, that is calcium oxide. The reaction is pretty similar to Ca plus O2 gives us 2CaO, which dissolves in water. CaO can easily dissolve in water. CaO plus H2O gives us CaOH twice, which can quickly turn the red litmus paper blue. The solubility of calcium hydroxide is more than the solubility of magnesium hydroxide, so it dissolves faster and it turns the red litmus paper into blue very quickly than in comparison with magnesium hydroxide. Up next is iron. It burns with yellow sparks and not with a kind of flame color. It gives us a blue-black solid, which is iron oxide, FeO. The reaction is pretty simple. 2Fe plus O2 gives us 2FeO, which is insoluble in water. And remember, if it's insoluble in water, we can't test it with the litmus paper. This is something that we have previously discussed under the heading of importance of water. So water is pretty significant. If there's water, an acid can act like an acid, an alkali can act like an alkali, but in the absence of water, both cannot happen. Next up is copper. It does not burn, it just quickly turns black. That's because 2Cu plus O2 gives you CuO, copper oxide, and copper oxide is black in color, as written black solid over here. Well, it's also insoluble in water, and as it's insoluble in water, we cannot test it with litmus paper. This completes the entire table for us. So you might have noticed that we have written a lot of reactions, but if a substance is insoluble in water, the effect of adding water cannot be written in a reaction. And of course, consequently, we won't be able to test it with litmus paper. Now this completes this table for us. The diagram at the bottom of the page needs to be re-understood once we're done with all the information of different metals and non-metals in terms of their oxides. Now take a look. Non-metal oxides are actually acidic oxides. Carbon dioxide, sulfur trioxide, all the ones which I dissolve in water can turn into an acid and can neutralize bases. On the other hand, metal oxides are basic oxides. Calcium, magnesium, copper, sodium, potassium oxides are all basic oxides. When dissolved in water, they act like bases. Even if they're not dissolved in water, they can always neutralize the acidic effect, and hence known as basic oxides. Now it's pretty simple. The ones that form acids upon when dissolved in water, or the ones that can react with the base, are acidic oxides. And the category of metal oxides which can actually react like a base against acid or can neutralize acid are the basic oxides. Well, there are two more types of oxides. Neutral oxides. Neutral oxides do not react either with acids or with alkalis as written over here. That's because they're probably insoluble in water and they do not react with acids or alkalis. So water itself, carbon monoxide and nitrogen oxide are the examples of non-metal oxides. Which brings us to the last type, amphoteric oxides. Zinc oxide and aluminum oxide are the examples of amphoteric oxides. Taking a look at the key definition in the center of the page, you would see the definition of amphoteric oxide or hydroxide. Amphoteric metal oxides or hydroxides are the ones that react with both acid and alkali to give a salt and water. So usually acids and alkalis react to form salt and water, which are the neutral substances. So what we say over here is that amphoteric oxides can do the same with acids as well as alkalis. Take a look, we have a couple of reactions at the bottom, and there are a couple of reactions on the next page too. I'll however like to go with the next page. Take a look. Zinc hydroxide, when reacted with excess of alkali, it forms salt in water. The salt is even soluble in water. So it proves with the help of example that zinc hydroxide or zinc oxide can react with sodium hydroxide and can react as an acid while reacting in this equation. So acid plus alkali gives us salt plus water. So zinc hydroxide plus sodium hydroxide gives us sodium zincate plus water. Well, these are some things explained and mentioned, but they don't exactly explain zinc oxide as an amphoteric oxide. By that we mean when it reacts with an acid, it reacts like a base. When it reacts with the base, it acts like an acid. So I'm going to write a couple of equations to make sure that you understand how zinc oxide can react with an acid to form salt and water. Take a look. Actually, not bad. It balances this way. So take a look. Zinc oxide plus acid gives us salt plus water. That means zinc oxide is acting like base. But as it's amphoteric, we might need to react it with an alkali and it forms a salt and water. So that's the reaction. Sorry, my bad. Na2ZnO2 plus H2O. Take a look in this reaction. Zinc oxide is reacting with alkali, forming salt and water, which means zinc oxide is reacting as an acid because acid plus alkali gives you salt and water. In the reaction written on top, zinc oxide reacts with 2HCl. So of course, zinc oxide is reacting with an acid, producing salt and water. So the neutralization reaction is complete. Whether the oxide reacts with acid or reacts with alkali, in both cases, it produces salt and water. Let's write the same reaction for aluminum oxide. Both of these reactions, actually all four of these reactions I'm about to write, have been a part of past papers. So it reacts in such a way it produces AlCl3 plus it produces H2O. So 3, and that's how we balance the equation. Take a look in this equation. Aluminum oxide reacts with an acid to produce salt and water, so it must be acting like an alkali. In another reaction, we can react it against the alkali NaOH, and it gives us this product. The equation balances somehow. I think I'm not able to balance the equation yet, but yeah, if you're going to try it, you would be able to balance it. So Al2O3 reacts with NaOH, gives us NaAlO2 plus it gives us H2O. So these are the four equations to prove zinc oxide or aluminum oxide is an amphoteric oxide. Remember, if a question like this comes in exams, you got to prove an amphoteric oxide by two reactions. It gives us salt and water on reacting with the acid. It also gives us salt and water upon reacting with the alkali. So it does almost the same. Moving back, this completes 5.3 for us. Any questions from the oxide part?
Sir.